This is Concept 2 Notes, and we are going to talk about electron configurations. So let's go back to the electron cloud. If you remember, because we've said it several times now, electrons are in constant motion, and they surround the nucleus of the atom, which is the electron cloud. But because they're in constant motion, it's hard to know where exactly they are in the cloud. And that's where quantum theory is helpful. It is a mathematical description for the wave properties of electrons and other tiny particles. Now, another term that's going to be important to know is orbital. This is a three-dimensional region around the nucleus that shows where an electron probably is. And something called quantum numbers, which come from that quantum theory, are used to describe these atomic orbitals. Now, I'm not going to get into these quantum numbers with you in this course. There's kind of four, the principal, angular, magnetic, and spin ones. It doesn't even come up as of now when I'm recording this. It's not even a topic that's on the AP chemistry exam. So we're not even going to spend time on this now, but do know that these exist and they do matter. But for the sake of not getting confused in a topic that can be confusing, we're just going to kind of leave it at that for now. But let's talk more about putting numbers and descriptors like that to the electron cloud in the orbitals so that we can predict where they are since they're in constant motion. Okay, so remember, we said it so many times, the cloud is divided into shells or energy levels because the shell divisions are based on the amount of energy of the electrons. Okay, and we number the shells. So you can say n equals 1, n equals 2, n equals 3. And if you remember from our last unit, that first shell, the one closest to the nucleus, that's our level 1. And then the next one out is level 2. The next one out from that is 3, etc. And each of these shells can only hold a max number of electrons. Now, within these shells, though, there are sub-levels to them. So there's some other divisions to them. You can subdivide them more. That hold certain amounts that are lettered. So we refer to them as letters. These are those s, p, d, and f orbitals. So again, we said on the last slide, an orbital is like a 3D region where we could predict where an electron is. So these shells have these orbitals within them. So the s orbital holds up to 2 electrons, the p can hold up to 6, the d holds up to 10, and then the f holds up to 14. Now, those numbers seem random, but then when we look on the periodic table later, you're going to realize that there's a pattern to them like there is for most things. So let's talk about that first energy level, n equals 1. That first energy level holds 2 electrons. Now, total, and you may remember this because when we look at the first period on the periodic table, you may remember that period 1 is hydrogen and helium, and it holds a max of 2 electrons. Now, if we're going to subdivide the shell, it only has one orbital in it, one of those 3D regions, and that's the s orbital, which we said on the previous slide holds 2 electrons. So first shell has one orbital, it's the s1, and it holds 2e. Now, the second energy level, or the second shell, think about period 2. We said period 2 elements have 2 energy levels, the first and the second. The second one holds 8 electrons total. Now, it has 2 orbitals, though. We could subdivide it into 2 orbitals, the s, which holds 2, and the p, which holds 6. So that's where that 8 comes from, an s orbital and a p orbital. Then the third shell holds up to 18 total because it has 3 orbitals. It has the s that holds 2, a p that holds up to 6, and then it also has something called the d orbital, which can hold up to 10. So 10 plus 6 plus 2, that's where that 18 comes from. Okay, so this is where the numbers are adding up. But again, I don't want you to get overwhelmed by this. There's going to be a pattern to help you kind of keep this straight. And then when I say these different configurations, this is where I'm not going to get into all the quantum numbers with you, but when I mean configurations, there's just different ways that these can kind of be configured. I mean, that's just the best way I can say it. And again, I'm not going to expect you to know all of that detail. So for my purposes, this is enough for us. Okay, so what does this have to do? What do these configurations mean? So the electron configuration is the most stable arrangement of electrons in an atom's electron cloud. So we're trying to just figure out what's the most likely arrangement of where these electrons are going to be. And electrons tend to do what makes them the most stable. So we're going to make predictions about where the electrons are. Now, there are a bunch of different ways that you can notate this. There's something called the orbital notation, where you actually draw, you have some symbols and you draw and show like which way they're spinning and their different configurations. I'm not going to teach you the orbital notation because again, um, it's a lot and I don't want to overcomplicate something that can already seem a little complicated. So we're just going to learn two ways here. And so one way we're going to learn is just the electron configuration notation. Which is just a shorthand way of tracking electrons in an atom and knowing where they are instead of having, again, to like draw a full Bohr model. The Lewis structure is great, but it only shows us the valence electrons. The Bohr model shows us all of them, but it's not really detailed enough. And it's a bit robust. This is a lot simpler. And the reason why this electron configuration, notation is helpful is because it represents the quantum mechanical model, which is more accurate than the Bohr model. We said that at the start of Concept 1 notes. The Bohr model shows electrons in these fixed orbits, which just isn't accurate. The quantum mechanical model, or that, electron cloud model that we looked at, is showing the electrons actually in their constant motion. And this configuration is just going to be a much more accurate representation of where the electrons are. So we're building on what we've already learned. Remember, electrons act like waves in addition to particles, and thus we can use the quantum theory to predict how they are arranged. Now, to figure out electron configurations, there are 3 rules that will determine them. Okay, and these are really important. So first is the Aufbau principle. It says that electrons fill the lowest energy orbital first. Therefore, they're going to start filling closest to the nucleus first and then move out. Now, what we're going to see, there's a pattern to this that you're going to see. This gets trickier the bigger the atom gets, because the bigger the atom gets, the bigger the cloud is getting. And thus, the farther away that the shells are from the nucleus. And so there starts to be some kind of like overlap with the orbitals and the energy levels and all of that. And we will kind of talk about that, but just know we're going to fill from the lowest energy level outward that way. Next is Hund's rule. Hund's rule says that orbitals of equal energy each get 1 electron before any orbital gets a second pair. So if you remember when we were doing our Lewis structures and we were drawing this, I said you needed to draw an electron on each side before you paired any up. This is kind of falling into that. It's because we're going to separate them each out. The reason this happens is because it helps to minimize that electron-electron repulsion. Remember, the electromagnetic force is attractive between opposite charges, like the positive nucleus and the negative electron cloud, but it is repulsive between like charges, like the two negative electrons. And so this helps to minimize that because we want to have the lowest energy possible. So we're going to basically think about, like, we're going to spread them out before we make them sit by someone. If you have a minivan and you've got 3 kids, you're going to put 1 kid in each row of the minivan before you force a sibling to sit by another sibling to kind of make it the least energy and the least drama ride to school as possible. Okay? And then the last rule is the Pauli exclusion principle. And it says that no 2 electrons in the same atom can have the same set of quantum numbers. So I told you that there were 4 different quantum numbers. And again, we're not going to get into them, but basically there's no way 2 electrons can have the same of those 4. So if 2e are in the same orbital and they're in the same space and they're paired up, they're going to be spinning opposite directions. And I know I'm getting redundant by saying we're not going to get into the quantum numbers too deeply, but again, I feel like it's a little bit much. So this reference to them, don't let it stress you out. But basically just means like they're all going to have their own numbers. No 2 can have the exact same. Okay, now this is where you got to participate. You need a periodic table that you can color. I want you to not be scared of this, and there's some patterns here, and so I'm going to point them out, and I want you to pause and color your periodic table before you go on to the next one so that yours can kind of match mine. All right, so first, looking at your periodic table, we said there's s, p, d, and f orbitals. Well, there's also blocks on the periodic table that match these. So first, I want you to color groups 1, 2, and helium all the same color. So I picked the seafoam green. You can pick any color. Just pick the same color for these things and make a key so you know. And this is going to be your S block. Okay, so these are elements that are going to have their final electrons in an s orbital. Okay, that's how they're going to end. And this will make sense as we start writing these out. Okay, and then next, we're going to color groups 13 through 18 minus helium is going to represent the p block. Okay, because these elements, their valence electrons, their final ones will be in a p block. All right, next we have groups 3 through 12. They're going to be colored as the d block. And then last, we have the lanthanoids and the actinoids, and they are going to be represented as the F block. Now, let me tell you something. The F block gets complicated, and there are actually a lot of exceptions to the off-bar rule that we just discussed in the F block, just because elements are so big and there just becomes a really small difference in the energy levels and like what's going on here. So just know that the electron configurations for these get tricky. I will never ask you to do one on an assessment. We do have an activity where there might be one or two, but I give you some clues to like help you figure it out because again, these get tricky and there are some exceptions. Now, another thing with this that is tricky and that there's some debate about is you know that all of these are supposed to kind of fit right here, but also notice that like this is colored orange. So it's like, are the LA and AC, are those the ones that go here? Or is it these, the LU and the LR that go here and then all the others are down here? Which like best follows the pattern? So technically, these two elements, 57 and 89, they don't have any electrons in the F block. So some argue that really LA and AC should go here and then all of these kind of like scoot behind them, okay? They should go up in the D block because they should be that 6D1, which we're going to see in a second. But another argument is if you look at the electron configurations of these two elements, element 71 and 103, we see something different. They have a D block electron. So some argue that these two elements should be up here, you know, in the D block. Others argue that these two should be up here in the D block. I have linked an article that I have that I can print out for you if you want to read this debate. I've looked at multiple chemistry textbooks and they all kind of show this differently. This periodic table and all the periodic tables I will give y'all is consistent with what is given by College Board to AP chemistry students when they take the test because I just want you to be seeing the same things as they are. And so that's kind of where I kind of made my declaration in terms of how to organize this. But I just want you to know that it gets tricky. Please don't stress about these. Anytime you have any questions about these, I will give you a hint and you'll never have a question on a test about it. Okay, so color those and I'll leave it at that. All right, now the next thing I kind of want you to do is add some labels to this. Now, you can draw, I have labels and arrows. You can draw the arrows if it helps you. It's up to you, whatever you want to do for your drawing. Just make sure you can still read your periodic table. Okay, so next I want you to label this. This is the 1s orbital. So we already know that period 1 is one energy level. We saw in our notes earlier that the first energy level only has one orbital and it's the s orbital. So the hydrogen and helium represent the electrons that go in the 1s orbital. All right, next would be the 2s. So there's two electrons that go here, and then 3s, 4s, 5s, 6s, 7s. So this is why this is the S block. It matches the period numbers. These are all the S's, okay? Now let's talk P's. This is the second energy level. This is the P block. So we refer to these elements as 2p, 3p, 4p, 5p, 6p, 7p. All right, the pattern kind of makes sense. Now let's talk about the D block though. This is where it gets tricky. So this is actually the 3D row, okay? It's not the 4D row based on how this is pictured. If you remember from our notes, I said that the third energy level has an S orbital that holds 2 electrons, a P that holds 6, and then a D orbital that holds 10. So these are down here, okay? So that's the 3D, this is the 4D, this is the 5D, this is the 6D. And then last, we have the 4F and the 5F, because remember, these kind of sneak in here. Now, again, you might be being like, why is it 6 and then 5 and then 4? That'll make sense in a second. Okay, so another thing that can be helpful with figuring out these electron configurations is you're always going to go left to right on the periodic table. Like if you just follow the periodic table in order when you're writing these out, it'll make sense. And I'm going to show you that in a second. But there's another way you can kind of double check if you did it right and you have them in the right order. Because we always want to write them in order of least energy to in the order that would require the least amount of energy for the electrons to be in that stable configuration. So this is called the diagonal rule. And basically, if you have a chart like this, which I will provide you on the test, if you kind of work diagonally down these rows, it will always go in the right order. So 1s first, then 2s, then 2p, 3s, then 3p, 4s, 3d, 4p, 5s. If you just go like this, that is the order it will go in. So you can always double check your work off this, but honestly, I just think if you have the periodic table like this, it's the simplest because you're literally just going to read from left to right. Okay? Now, let's talk about how to actually write these so you can have context for what the heck I'm talking about. Okay, so first thing, if you're going to write the electron configuration, aka you're going to write the arrangement of all the electrons in an atom, here's what you're going to do. First, you'll write the number of the shell that the electrons are in. Then you'll write the letter of the orbital. Then you will write the number of electrons in that orbital. It will be a superscript. Then you will repeat until you run out of electrons, and then you need to double check your work, either by looking at that periodic table or looking at that diagonal rule. Okay, so let's do an example. Let's talk about hydrogen. You probably remember, if you look at hydrogen on the periodic table, its atomic number is 1. It has 1 proton, which means it has 1 total electron in all of it. Okay, so that 1 electron, where will it go? We'll look at the periodic table. Look at where hydrogen is. Look at where we colored the blocks. The number of shell is 1. The orbital is s, where hydrogen ends up, and there's only 1 electron there. So we would put a little 1 there. 1s superscript 1. That is the electron configuration for hydrogen. So you have your number of shell, the letter of the orbital, and the number of electrons. Okay, let's see how helium's is different. Look at helium. What's the number of the shell that it's in? Okay, look at your periodic table. It's in 1s. Okay, so that's your 1 and 2. That's your number and your letter. It's in 1s. And then the number of electrons. Helium's number 2. It has 2 total electrons. The s orbital holds 2, so 1s2. All right, let's keep going. We're not going to do the whole periodic table, but I want you to keep seeing the pattern. All right, now let's do lithium. Look where it is. Okay, first, remember we have to start at the beginning because you have to fill from the inside out. That's one of the rules. So we start at 1s. So lithium is atomic number 3 that has 3 protons. That means it also has 3 total electrons. So 2 will go in that 1s2 orbital. And then when you get to 2s, there's only 1 left. So if you add up the superscripts, that's 3. That's the atomic number of lithium. That's the total number of electrons. Remember, we keep going until we run out of electrons. All right, let's try nitrogen. Honestly, you can put your finger on the periodic table right now and then just draw your finger across it, and that's going to help you figure out the configuration. So start at the top. We draw our finger all the way across from hydrogen to helium. That's 1s, and there's 2 of them. So 1s2. Now go to the next row. We're in 2s. So 2s, and then let's count 2s2. 1, 2. All right, so write 2s2. And then if we keep moving our finger, we get to 2p. Count to nitrogen. 1, 2, 3. So it's 2p3. 1s2, 2s2, 2p3. Add those superscripts up. You get 7. Nitrogen's atomic number is 7. That's how you know that you filled it in right. So this is how the electrons are configured in the electron cloud of a nitrogen atom. This is the specifics of where they most likely are, even though they're in constant motion. Okay? Again, this is one of those things that, like, when you're saying it and you're looking at it, it sounds so complicated, but when you actually start doing it and just literally moving your finger across your labeled periodic table, it's going to be a lot easier than you think. Okay, so I want you to take a minute and I want you to try this for these 5 elements, and then we will go over them. Now, for the sake of the notes, as you get going, you're going to be like, what happens when I get to period 4 on? Because that's where we start seeing it goes 4s, 3d, 4p, 5s, 4d, 5p. Like, it starts getting a little confusing, okay? Remember, based on the Aufbau principle, electrons are going to fill the lowest energy orbital first. And so what happens is the 4s sublevel, that orbital, has actually slightly lower energy than 3d, which is why it goes first. So technically, the 2 electrons will put themselves in the 4s before they start filling the 3d orbital. It gets filled first, again, because E always fills the lowest energy level and the most stability. Okay? Now, transition elements, too, they transition because their s and their d orbitals, these start getting so close together in energy that, like, electrons can be lost from both of those levels. So that's like zinc can have a +1 charge, a +2. Like, it can lose 1 electron, lose 2 in a bond. Like, it does different things. That's why they're transition ones. They can do different things. But that's because, again, these levels are really, really close. So they're not always losing valence electrons. Sometimes they're losing ones from their other orbitals as well. Okay, so that's kind of the backstory. Again, practically speaking, though, don't stress about this, because as long as you just go in order, you're not going to ever get them wrong. Okay? Now, what you may have noticed when you were doing that last practice is that as you got to ones like, gold and xenon, you're like, golly, this is getting long. This is a lot to write. Well, there's a shorthand notation that we can use of our shorthand notation, and that's the noble gas notation. So this is just an abbreviated way to write these electron configurations. So basically, all you do is you go to the symbol of the previous noble gas, and then you just write the electron configuration from there on. Okay, so for example, calcium. Look at calcium on your periodic table. It is element number 20. Now go backwards. What's the closest but like most previous noble gas? It's argon. Argon has an atomic number of 18. Okay, so what you would do for the noble gas notation, instead of writing 1s2, 2s2, 2p6, 3s2, 3p6, you would just write argon in brackets. And then from argon on, you just write what's left, which would be 4s2, which is where we end up with calcium. Okay, so you have the previous noble gas that was there, or the prior noble gas, and then whatever's remaining of the electron configuration. So it just saves you from having to write out the whole thing. Okay, so same elements I had you write the electron configuration out for before, but now I want you to write the noble gas notation for each of these. So write kind of like the shorthand of each of these. Okay, and we'll go over these, and then we're going to do lots of practice and a fun activity, and I will make sure that you are a pro at electron configurations.